problems. He has participated as a workshop instructor at the CORE 2024 conference, where he led the workshop Algorithms on Quantum Computers. Additionally, he has been part of the organizing committee for the Science Outreach event Qiskit Fall Fest 2024 and has participated in the Quantum Computing Mentorship Program of the Quantum Open Source Foundation. I give the word to Jorge Saavedra.
Yes.
Perfect. Then I give the word to Jorge Saavedra.
Okay, thank you for the introduction. So, as the title of my presentation says, I'm going to talk briefly about the analysis of quantum approximation algorithms for combinatorial optimization problems. Next, please. Next. Okay. What is the motivation for addressing combinatorial optimization problem using quantum hardware? That is because some of combinatorial optimization problems, such as the knapsack problem, max code, portfolio optimization, are NP-hard problems, right? That means that there is no classical algorithm that allows us to get a solution of that problems in a polynomial time. So for large instances, those problems becomes computationally unfeasible. So there are many methods that have been explored, such as heuristics or approximation methods, but the disadvantage of that methods is that they can be trapped into local minimum for complex instances. So nowadays we have new tools as quantum computers that offers a different way for solving these kind of problems. So we can take advantage of some of the properties of this quantum hardware, such as quantum superposition and entanglement, to tackle these hard problems. The problems that I'm going to talk about are designed to work on near-term quantum hardware, the current hardware that we have. Next, please. If the roadmap for solving this kind of problems are familiar to you, you probably know that the first step is to transform our combinational optimization problem into the cubo form. This is just a representation of our cost function in terms of binary variables in a matrix Q that contains all the information of our problem. Next, please. Many problems are subject to inequality constraint and equality constraint that must be introduced into the cost function, into the cubo form. So it's easy when we deal with equality constraints, because these constraints are just introduced using a quadratic term. But when we deal with inequality constraint, it is more difficult because of the restriction of the cubo form, that we only have access to quadratic expressions. So A well-known method is to use slack variables. The disadvantage of using this method to introduce inequality constraints into the cubo is that um, this method increase the number of binary variables. And this means that if each binary variable is represented by a qubit, we will have more qubits. And we don't want this because uh, we 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 are interested to use uh, less uh, the less resource as we can, and qubits are not the exceptions. So uh, another newer method that has been proposed into the state of the art is using unbalanced penalization that um, it allows us to introduce inequality constraints using a quadratic expression. This means that it has a linear term and also a quadratic term. Next, please. Okay, once we have introduced inequality or equality constraints into the cubo, the next step is to transform uh, the cubo expression into new expression that can be handled by the quantum computer, right? So for this purpose, uh, we need to transform the binary variables that we have, 0 and 1, into the new spin variables, -1 and 1. And this transformation can be done just uh, changing, uh, just with this transformation that you can see in the slide. Just change the x binary variables into the new um, variables, spin variables. Next, please. Okay. Uh, Now we have our problem expressed in a way that the quantum computer can deal with it. So I'm ready. We are ready to try to solve this problem using quantum hardware. And there are many architectures that allow us to tackle these kind of problems. Uh, One of the first uh, approaches that we currently have um, is the quantum annealing. Quantum annealing is a method based uh, on thermal annealing. Thermal annealing is a classical method based on metallurgic. This algorithm allows us to find the minimum state of a metallurgic system. The first step is head the material, head a metal, and then slowly cooled this system. This system at the end of this heat and cooled process that I have mentioned before. That is the quantum tunneling. And probably this property is unfamiliar to you because of the most recent Nobel Prize of Physics. So we can take advantage of this quantum tunneling to explore more uh, feasible solutions when we are evolutioning evolving um, these systems, right? So this quantum algorithm allow us to find the ground state of our um, cost function and now express it in a cost Hamiltonian. And for this purpose, we can use quantum annealing specific hardware, such as the hardware provided by the company D-Wave. You can see an example of the quantum hardware uh, in the image in the current slide. This is the newest uh, quantum computer that this company provides to uh, to use for solving these combinatorial optimization problems. Next slide, please. Another group of methods that are used to solve combinatorial optimization problems with quantum hardware is the family of variational quantum algorithms. This family of quantum algorithms is based on the variational principle. The variational principle states that the ground state of a system described by a Hamiltonian, such as our cost Hamiltonian that we have of our problem, is bounded by the expectation value of this Hamiltonian with respect of any normalized trial function. So it means that it doesn't matter what is the trial function that we use to compute the expectation value. Uh, the ground state is always the minimum state that can be reached. So next slide, please. This is the general uh, workflow when we uh, when we deal with um, uh, variational quantum algorithms. The process starts, as I mentioned, with a combinatorial optimization problem. Then we convert the problem into the cuboform, and then we can transform the cuboform into the Ising Hamiltonian, which we are going to be interested to find the ground state of that Hamiltonian. And then um, we initialized uh, our our triad function. Uh, this triad function can be expressed using uh, quantum circuits, and then we compute the expectation value of our cost Hamiltonian. This process is an iterative process where the the state, the trial state, uh, is going to be uh, optimized, classically optimized, in order to find the state that minimize or that allow us to get the ground state of the Hamiltonian. And once we reach, for example, uh, the number of iterations, we finally measure how good was the solution. Next slide, please. One example of uh, one variational quantum algorithm is the well-known BQE. BQE is from a variational quantum eigensolver. BQE uh, constructs our trial function using variational parameters. The variational parameters are the thetas in the expression. These variational parameters will be optimized using classical optimizers, and the trial function can, as I mentioned before, uh, can be uh, constructed using a quantum circuit. There is a general quantum circuit for the BQE. BQE use single qubit rotations followed by entangled gates to construct the trial function. Next, please. Another uh, algorithm, another example of variational quantum algorithm is the QAOA. QAOA from quantum approximate optimization algorithm is um, another variational quantum algorithm that allows us to construct a trial function, but this trial function is based on the information of our Gauss Hamilton. Uh, it's pretty similar to the BQE that we saw before. Next slide, please. And um, there are, in this slide, we have just a little details of how we can construct the quantum circuit of this variational quantum algorithm. But I think because of time, we can go to the next slide, please. Next slide. So here is a analogy that I would like to present to you. This analogy is to explain uh, variational algorithms in using a more visual way. If you know this device that is in the slide, um, uh, you can know that this is the Galton board. The Galton board is just a device that in which we have a bowl with balls, and then we deliver the balls, and because of gravity, it will uh, fail, and then the distribution that we have at the end of throwing of released all the balls is the normal distribution. Next slide, please. But using this schematic example, we can view a similar way of how variational quantum algorithms works. First, the ball, the shape of the ball represent the quantum circuit initialization. We can change how we initialize our initial state. Then we have an ansatz with variational parameters. These variational parameters are represented with pegs that we can change the size of the pegs and the form of the ansatz, putting more pegs or less pegs. At the end, we have uh, a distribution that it represents the measurement at the end of the variational quantum algorithm. So I think that this visual way is um, can be helpful to understand uh, how variational quantum algorithms works. Um, and I think we have more slides. Uh, Next, please. And there are just some limitation and opportunities uh, of quantum of variational quantum algorithms, and also include the quantum analytic. But the time is over, so thank you for your time, and I hope you enjoyed the presentation or learn something new or a different perspective how these algorithms works. So thank you.